The next application of projection operators is very, very useful and shows up all over quantum physics and classical physics whenever problems are linear and composed in terms of matrices or operators. And it's called spectral decomposition. It follows from the Hamilton-Cayley formula that if you multiply projection operator, which has all factors of m minus eigenvalue in it, by m minus eigenvalue of this projection operator, it follows that this is zero by Hamilton-Cayley, or by application of m on pi, we get Li, so we get zero term. That implies that if you apply matrix M on a matrix which is a projection operator corresponding to the ith irreducible subspace, this matrix, no matter how large, simply returns a single number which is its eigenvalue. Now write M as M times identity and replace identity by the completeness relation, and we get an expression for M in which M is a sum of matrices, each one of them being projection operators, just multiplied by causal coefficient, which is the eigenvalue. And the number of terms in the sum is the number of distinct eigenvalues. Each eigenvalue owns its own R-dimensional subspace. Any matrix function can be expanded as some sum of m's to the various powers and coefficients. M acting on each subspace gives me f back. We get the spectral decomposition formula. Spectral decomposition is a wonderful formula which you use all the time whenever a problem can be cast in the language of linear algebra, either matrices, which you are familiar with, or in terms of operators, which are morally also matrices, but they're very large or infinite dimensional. It replaces left-hand side, which is some homologous matrix or operator in some quantum mechanical calculation, let's say, by a sum of ordinary function evaluated at the corresponding eigenvalue of that operator. This is an enormous saving. And this is the reason why nobody by a fool would ever not use irreducible representations if they're available. And this is the reason why from get-go, day zero, they teach you quantum mechanics in some very mysterious language of operators and i's and h-bars and momenta being derivatives and God knows what. And they do it because it would be foolish not to do it, because spectral decomposition, written out here, where lambda I is, for example, eigenenergy of a Hamiltonian quantum system, it was just foolish not to use it. But it's not quantum mechanics. All of it's 19th century algebra, linear algebra matrices.